All right, well, welcome back to another fun-filled day of stats. We are now starting week number 2, and the goal today is actually to finish up. There are a few more terms from chapter 1 we need to discuss just so that you're familiar with them. And then we're going to move into chapter 2, which is really looking at how do we deal with data, right? Once we have our data, what do we do with it? And that's going to be a lot of what we talk about in this class overall. But today we're definitely going to be looking at specifically some graphical, some visual methods for displaying the data that we collect. But before I dive into that, there is homework due tonight, the first set of homework. And so I just want to open it up to any questions on that. Anything that we need to talk about that you're unsure of?
Hold on, you said that there's homework due tonight?
Yeah, I thought it was the.
Is it actually the following Tuesday?
Yeah, that's what it's listed at.
Okay, well, then whatever it's listed on in Canvas is correct. I just know I made it Tuesdays. I guess I thought there was one due today, so never mind about that. But still, if there are any questions on what we talked about, I'll be happy to go over it. But thanks for catching that, guys.
So population, that's like the big one, and then parameter is what you're taking from the big group, right?
Okay, so population, yes, is the entire group that we're looking at, right? Mm-hmm. So it's not just the sample. Remember, the sample is the smaller piece, yeah. Smaller group, right? Yeah, but so population is the entirety. And actually, real quick, can I get your name? Because all it's showing says iPhone, and I'm not sure what your name is.
Oh, sorry. Yeah, my name's Mason Yonker.
Okay, that's cool, Mason. Thanks. I just like to know who I'm talking to.
Yeah, sorry.
No, it's all good. Excuse me here for a second. My dog was doing something.
Google, and it kind of messes it up, I think. I'm not sure.
Oh, no, that's no worries. Absolutely no worries. Okay, so you're right that the population is our entire group, right? And then the parameter, that's the number, that's the quality, it's the thing that we're trying to describe for that population, right? So like one of the ones we were talking about was last class were the ages of first-year college students, right? And so in our class, we took those of you that were first years and you gave me your ages. And so we got a sample. But if we are going to be looking at that, the average, let's say the average age of first-year college students overall, that's the parameter.
Okay.
Right? Where the average age of the students in our sample, that's the statistic.
Okay. Okay, yeah, thank you.
All right, cool. Thanks for that question. Other questions? All right, so it sounds like we're feeling pretty good and you guys seem to survive the horrible day of terminology thrown at you, so I'm glad to see that. So I just have a few more of those we have to take care of, and then we'll dive into actually talking about how we do statistics. All right, so I'm going to go ahead and hop up to my whiteboard then, so give me just 1 second. I'm going to switch screens and I'll be back with you in just a moment. And as promised, I know some of you guys were talking Star Wars, and so I told you I'd wear one of my favorite Star Wars shirts. So here you go. Father, Son, Holy Spirit.
Nice.
You'll definitely see a few more as the quarter progresses. Anyway, all right. So some more terminology that we need to talk about just in terms of statistics and sampling and all that good stuff. So first, let's talk about replacement versus non-replacement. Okay, so when we sample, you can actually you can sample in one of two ways. You can sample with replacement, and you can sample without replacement. All right, now the best way to kind of explain this, I think, is using cards. A lot of us play card games of various types, and cards are a great way of showing sampling. Okay, so I've just got a deck of cards here, standard deck of cards, nothing fancy about it. Right, so imagine I've got this deck of cards and I want to just get 5 cards from it. So I'm going to sample. I'm going to take a sample and I'm going to take 5 cards. Okay, now with replacement and without replacement are like this. So without replacement is how you think about taking 5 cards, right? I hold this deck out and I say take 5 cards. So you go, okay, well, there's 1, there's 2, here's 3, here's 4, and there's 5. All right, so I just dealt myself a 5-card poker hand, and you take a look at it. It's not that great of a poker hand, but there you go, right? So I have a 10 of spades, a 10 of clubs, 8 of hearts, 7 of hearts, 8 of diamonds. So we just took a sample of 5 from the population. The population is the entire deck, right? This is my sample, my 5-card hand. And so I took this sample from the population. Now, maybe I'm going to measure it somewhere. I'm going to take the average value of these. And so this is the, and so I would look at those 5 cards, take the average of their numbers. And okay, so there's my average for the sample. Okay, well, I could, if I put them back in, so we're back to our population, I could draw another set of 5, right? So we'll just shuffle it up to be good about it. All right. I'll take another sample of 5. So 1, 2, 3, 4, and 5. Right. So here's another sample. It's a different sample. Right. In fact, it's a very different sample, but not entirely different. This is pretty crazy. I wasn't expecting this. I don't know if you noticed, there is a card in common in this sample that was in the other sample. Anybody catch it? You might not have been paying close enough attention.
Hey.
But it's that sucker right there. 7 of hearts was actually in the other set too. Go figure. Anyway, all right, well, so here's a different sample of 5, but again, done without replacement. Now, why was that without replacement? Well, every time I took a card, right, so I just took this card, Ace of Hearts, out of the deck, I set it aside. So now I don't have 52 cards to pick from. I've only got 51. Right? So I go and I draw another card and I set it aside. I don't replace it back into my population. So now my population is down to 50. Now there's 49. Now there's 48. Now there's 47. So when you sample without replacement, when you choose an element to be part of your sample, it's no longer part of the population that we draw from anymore. All right, so that's without replacement. All right, well, ooh, oh, this was the hand I was waiting for. Hanging out. Dealt 3 5s with an ace and a king. Hard to beat that one. All right, anyway, so that's drawing without, sampling without replacement. Now, with replacement means we do this. So I take a card, I draw it. All right, so in our sample is the King of Diamonds. But then the King of Diamonds goes back into the deck. And you can see it's right back there in the deck. So now I go and I draw another card, 3 of diamonds, put it back into the deck. Then I draw another card, 7 of hearts, put it back into the deck, and so on. All right, and so that's sampling with replacement because I'm taking that element that I just sampled and I'm putting it back into the population. All right, so let me just go ahead and write down here what's going on with those. So sample with replacement, you return the sample element back into the population. Before sampling again. Right, so I took that card out of the deck, slide it right back in. So that's sampling with replacement. Sampling without replacement is we remove the sample element from the population before sampling again. All right, so these two, I mean, they're pretty easy to understand. They make a lot of sense, right? Sampling with replacement versus without replacement. Now, in terms of which one you're going to do, it kind of depends, but usually we sample without replacement, right? Like, let's say you're going to go and you're going to go ask people their opinions on, you know, the University of Alabama football team. I'm just bringing them up because they just won the championship yesterday. I don't care for Alabama. Anyway, so let's say we're going to go ask people their opinions. So you go and you ask me my opinion, you get your information, and you move on to somebody else. You're not going to come back to me and ask me my opinion again, right? So usually when we do this, we sample without replacement. However, that's not always the case. And sometimes there is sampling with replacement. And a great example there would be, let's say we're interested in the size, the lengths of kokanee that are in Lake Tahoe. So for those of you who don't know, kokanee are a fish. They are a trout, and there are a bunch in Lake Tahoe. All right, so we go out, we catch a bunch of kokanee, we measure them, and we release them back, right? We're going to catch and release. That's sampling with replacement, right? I just took that fish, let's call that fish Bob. So I just took Bob, I measured Bob, and I let Bob go back out into the water. So then I go out and I catch another fish. It's possible that I'm catching Bob again, right? It's possible, probably not, but it's possible. But the point is, Bob got put back into the population before I sampled again. All right, so replacement versus non-replacement, that's the only difference. Now, it does change things mathematically. It does change things mathematically. Come back to this deck of cards, right? So I go in here and I draw a card and I get the Ace of Clubs. Okay, so Ace of Clubs is my first card. Now, think about if I don't replace. So I take the Ace of Clubs and I set it down over here. I go in here and I draw another card. This time it's the Four of Spades. So you think about what's the chance of me getting the Four of Spades? Well, there were 51 other cards left, right? And so that Four of Spades lies within that 51. So in terms of getting a card different than the Ace of Clubs, I'm guaranteed, right? Because there are 51 of them in here. But the chance of getting that Four of Spades, I lost the Four of Spades, so we'll go with Two of Spades. The chance of getting Two of Spades is 1 out of 51. Now, let's put the Ace of Clubs. We draw the Ace of Clubs, we put it back in. What's the chance now that I draw this Two of Spades? Well, it's not 1 out of 51 anymore. Now it's 1 out of 52. So I've changed the likelihood of getting the same sample that I had before. And in fact, there's also non-zero chance that I draw the same card again. All right, so it changes the numbers on things. However, I'll just tell you, here's the good news. If our population is large, not 52, but if our population is large, like the population of South Lake Tahoe, right? Maybe we're going to talk to people in Tahoe, or you want to go bigger, let's go to the state of California, or even bigger, let's go to the entire United States. If I was going to go and randomly pick 10 people from the United States, so we're going to list everybody, you know, we put them into a hat and draw their names, and I draw 10 people with replacement or without replacement, it's going to be virtually the same likelihood that I draw that set of 10, right? I mean, just think about it. You go and you draw my name out of the entire list of all names of everybody in the United States, and then you put my name back in there, shuffle it all up, and draw again, the chance that you draw my name again, oh, minuscule, right? Well, there's like 350 million people in the United States, so it's a 1 out of 350 million chance. It's not going to happen. It's very unlikely. So if our population is large, we don't have to worry about this. However, we deal with small populations sometimes, right? So it's just something to be aware of. All right, so are we good with this? Give me a thumbs up if you get the idea of replacement versus non. All right, awesome. Seeing lots of thumbs up, appreciate it. All right, so that's replacement versus non-replacement. Another term that's gonna come up, and it's gonna come up later today, assuming we get there with our time, is the word variation. All right, now this is another one that makes a lot of sense if you just think about what the word means. So in everyday use, what does it mean if things vary? What does that word mean to you?
Change.
Okay, so they're changed. There's difference, right? If something's variable, it changes. And so this variation is a property of change, all right? And in statistics, what it is, this is a measure of the difference in the data. So remember last time when I asked you guys about the age of first-year college students, and a lot of you threw out the ages there. You may remember that those numbers were all pretty similar. We had 117, we had 119, and then the rest were 18s. So there were like another like 5 or 6 that were 18s. That set of data did not have a lot of variation, right? The difference in the data was not much. But suppose we'd asked that same question. I asked that same question, and we had some other people that answered. And so we get the 17, the 5 or 6 18s, and 19. But then we also get a 24 and a 31 and a 58 and a 72. Now that set of data would have a lot of variation because there are lots of different values that we're getting. It's really spread out. And so that's what variation is. Okay, so in general, this is variation. But then there's also just variation, not just in the data, but there's also variation in the sample. And this is what it sounds like. This is a measure of the difference in this in samples. Because if we go to that same first year college student age thing, we'd had a sample from our class. But if I were to go to another statistics class at Lake Tahoe Community College and ask the exact same question, I'm probably going to get slightly different answers. Like let's just go to, we're going to ask for the average. So we take all those numbers and add them up and divide by the value to get an average. The likelihood when I go to another stats class that I get the exact same average is low. It's probably going to be similar, or hopefully it's similar, but it's going to be different. And so this is something else we have to realize, that not all samples are going to give us the same statistic. We might get different values. And so that's variation in samples. So one of the things that we are going to try to keep track of is what kind of variation do we have. All right, so there's variation. All right, so now another thing that we have to worry about are variables. So we already talked about variables. What's a variable in statistics? You remember what the variable is?
It's the characteristic that we are measuring.
All right, so it's the characteristic that we're measuring, right? So it's the, excuse me, it's the thing that we're interested in. the age of the student, the length of the fish, right? Okay, so here's an example of, let's say, a study that we want to look at. So here's the question. Does root beer consumption play a role in beard growth? All right, so maybe we're just curious. Do people that drink a lot of root beer, do their beards grow faster? All right, so I know it's silly. Nobody probably cares about this, but let's just say that this is our question. Okay, so what's the variable in here?
Beard growth.
Okay, so yeah, so beard
I'm
growth,
just not fast enough.
right? We're definitely curious in how is our beard growing. Okay, so this right here is a variable. But it turns out there's another variable in here. So I was a little misleading when I said what's the variable, because there's another one. Somebody
Beard
just jumped in.
length?
No, not the beard length.
The amount of root beer consumed.
There you go. How much root beer are we actually consuming? Right? Because if we're going to do this measure, or this study, we're actually going to measure both of those things, right? They're going to come to me and they're going to go, okay, Bruce, how much root beer do you drink? Right. So they'll have a number for it. It might be, you know, how many gallons of root beer or whatever, but or you know, how many times per week do you drink root beer, whatever their question is. But that's information they're going to get from me. Right. And we go, I drink root beer 5 days a week. Okay, so we write that number down. But that's not the only thing they're going to be curious about. They're also going to be curious about my beard growth. So they're going to measure that, however they measure it. Right? Take the length of my beard hair, compare it to what it was a month ago, or what, however they want to measure it. So it turns out in this case, there are actually two variables because there are two things that are being measured. Now, this sort of thing happens all the time. Think about like with this in our world right now with the COVID and the vaccine. They did lots of studies looking at vaccine. And one of the variables was probably for sure the ability of the body to create antibodies for COVID, right? But then the other variable was going to be, I don't know, how much of this specific thing we're introducing to them or however their study was set up, right? But you got two variables. But these two variables are not the same, right? They're not created equal. And so we have different names for them. So this one, the root beer consumption, this is what we call an explanatory variable. Okay, so think about what explanatory means, explain. An explanatory variable is a variable, a quantity, a thing, that prompts the other one. That is affecting change in the other one, or maybe not affecting change, but we think might be. The other one here, the beard growth, this is what we call a response variable. And again, that word makes sense. Think about when you respond. That's when you react to something else. And so in this case, it's does beard growth change with root beer consumption? If someone drinks a lot more root beer, does their beard grow a lot faster or fuller or however we want to describe it? All right, so if you're going to do a study, what you're going to do is you're going to change the explanatory variable. And you're going to see, does that have an effect on the response variable? All right, now it turns out that when we're doing something like this, there are probably a lot of other things that affect beard growth than just root beer. Right? Even if, let's just go under this assumption that root beer consumption does affect beard growth. All right? Probably. But let's just say that it does. Is that the only thing that's going to affect how quickly a beard grows? No, I'm quite certain it's not. Right? Probably hormone levels in the body affect it. There's going to be a genetic component to it, right? An age component, all kinds of other stuff. And so when you do a study, if you're really trying to figure out is root beer the cause, then what you have to do is eliminate all the other stuff, right? Now, those other things that might be affecting it are what we call lurking variables. Okay, and so what these are things that can affect the response variable. So those are those other things that we're just not really sure about, and that's why they're lurking, kind of lurking in the background, ready to make their change. Okay, so those are lurking variables. And so what we really try to do is we try to eliminate these. That's the goal of any good study, is to try to eliminate these. So this is when they would do something like, all right, we're going to look at root beer consumption versus beard growth, but we're going to look at only white men between the ages of 45 and 50. All right, so think about what that does. If we say we're only going to look at white men between the ages of 45 and 50, we're eliminating things like age playing a role, because all of our people in the sample are the same age. We're eliminating racial background if it's only white males that we're testing. Right? It's eliminating gender. And beard growth tends to already eliminate gender, but this definitely does, right? We're looking at males, right? And so a lot of studies will do that. Well, they'll say, well, we're only going to look at students who are taking calculus in high school. All right, we just narrowed it down to a specific group and we lose a lot of those lurking variables. All right, so you try to eliminate these. And then the other thing that we always do when we're doing this kind of sample or this sort of study is we create what's called a control group. And so just so you know what this is. A control group, this is a group that when we test, like in this case of root beer consumption versus beard growth, this would be a group that's actually not consuming beard growth or root beer. They're not consuming root beer. They might think they're consuming root beer, but we don't actually do that. And basically what that does is it gives us a group that is a standard that we can compare against. All right, so control group, this is just a standard that's used for comparison. So they're kind of the measuring stick, right? They're the metric. That's what we use to compare. And so again, go to this whole idea with the vaccine. There were definitely control groups. There were people who probably thought they were getting the vaccine, but they weren't. They were getting what's called a placebo. And that group was used as the baseline measurement to compare groups who were getting the vaccine to see if it was effective in creating the antibodies. All right, so there are all kinds of other terms involved in studies. I don't really want to go into more of them because I know you're probably already bored to tears. But probably the one other one that you should probably be aware of is what's called a blind study. In a blind study, they don't let the people being tested know, right? Like you don't know if you're in the control group, you don't know if you're given a placebo or the real thing, or you're given a certain dosage. You don't know. That's what it means for it to be a blind study. You can also have what's called a double blind study, which means the researcher, let's say I'm the one doing the research, I don't even know who's in which group, right? Like I might look over here and go, okay, so I've got Magdalene's in my group over here, but I don't know if she's in the placebo group, in the control group or not. Right? And that would make it double blind. Right? It's blind on both sides. All right, well, all of this is done. All of this is done when we create our sampling to try to actually get accurate measurements of the population so that our research is worthwhile, right? You don't want to go through all this. You don't want to do a study and then not get anything from it or not get anything useful from it. And so there's a lot behind it that we do to try to make it good. All right, now, for those of you who are going to end up going further in doing this sort of stuff in later life, you'll learn that. You'll take classes on this. Like just so you know my background, I was a math major who then dabbled in marine science. My first graduate program was in marine science. I was looking at how tides move sediment. It's pretty exciting stuff. All right, so I was looking at how tides move sediment, but as part of that program, I had to take a statistical design class to use specifically for marine science. And so I learned a lot of this stuff when I actually got there. So depending on what you're doing, you'll, if you end up being someone who uses statistics regularly, you'll learn all this stuff. But I just wanted to give you the real quick overview. All right, so before we dive into actually how we represent our data, any questions on anything I've talked about up to this point?
So I have a quick question regarding sampling.
Sure, Ashton.
What's the difference between sampling and probability, or are they all like rooted together?
Okay, so sampling is the actual act of choosing a sample and to do your study on. That's what we mean when we say sampling. Probabilities, those are the likelihoods that something would happen.
Okay.
Okay, so like I could say I'm going to do simple random sampling. I'm going to create a 5-card sample. I'm going to a sample of size 5 from this population of 52. And I'm going to do it, or I'll do it convenience. So 5 off the top.
Okay.
That was convenience sampling. So that was the act of sampling, was creating the sample. But the probability would be more like, okay, well, what's the probability that this is the sample that I get?
Okay.
And there we would have to look at what are all the possibilities and how many of them are this.
Okay, that makes sense.
Okay, so probability is just a measure of likelihood that something happens, and sampling is just the act of collecting your sample.
Okay, cool. Thank you.
Yeah, you're welcome. Any other questions? All right, well then let's talk a little bit about how we actually organize our statistics, our data, and stuff like that. So just to remind you of the different kinds of data that we can get, there really are 2 main classifications. And so the first was what we called qualitative. And the other one was quantitative. So what was the difference between those two? What's the difference between qualitative and quantitative?
Numerical and non-numerical.
Good. So the quantitative, this was the one that was numerical. So we get numbers for it. Qualitative was the non-numerical. So examples was like eye color, right? If we just go and we find out everybody's eye color, we're getting data, but it's not numerical, as opposed to getting their height. That's numerical. All right, so qualitative versus quantitative. All right, so we're going to talk about the difference between these two in terms of how we describe them and share their information. But there's also a little bit of a difference here in what we call the level of measurement. So let me just share this real quick before we dive into the data collector or data description for these other guys. Okay, so in terms of level of measurement, there are actually 4 different scales. The first one is what we call a nominal scale. And what a nominal scale is, this is just a list with no ranking. And you can actually do this with qualitative or quantitative, but this is just where you say, well, I've got a list and there's no rank. This tends to be more in a qualitative kind of case, where you just go, all right, here is the list of people's favorite colors. Right? There is no ranking to it, so we call this nominal. Okay, the next one that you can get is what's called an ordinal scale. And this is a list with ranking. A really good example of ordinal would be one of the ones like, if you've ever done like student evaluations, you know how you'll get it'll say like, how pleased were you with the instruction you received, or how was the instruction that you received? And you'll get things like excellent, good, average, poor, fair, poor, right? You know how you can get those. That's an example of an ordinal scale. It doesn't have to necessarily be numerical. It can still be qualitative, as long as there's some sort of a ranking. Okay, so nominal is just a list. Ordinal is it's a list, but there's a hierarchy. There's some sort of an order. Ordinal scale. Use the words to help you. All right, so you can have ordinal scale. You can also have what's called an interval scale. Now, for an interval scale, this does need to be quantitative. So I'm going to put a little star by it, and a little star here by quantitative, just so you know that this has to be really, it's really quantitative. All right, and so what this is again, the data is ordered. But differences can be calculated. I'm going to put here calculated and compared. Okay, so this is an interval scale. Before we actually talk about interval scale, I want you to notice what's going on is every time we move down this list, we're adding something else, right? Nominal scale is just a list. Ordinal scale, it's a list with a ranking. interval scale, it's now a ranked list, it's an ordered list, but also has this next property. All right, and it has the fact that differences can be calculated and compared. All right, so if we want to look at two different quantities, we can see how different they are, and we can compare that difference to anywhere else on the list. And a really good example of that is temperature. Right, whether we're talking Fahrenheit, Celsius, whichever one you're familiar with the best, it doesn't really matter. But as a sciencey guy, I go to Celsius. But let's just think about it. If you were to compare two temperatures, can you tell the difference between them? Yeah, easily. Just do a subtraction, right? What's the difference between 25 and C and 20 C? It's 5 degrees C. What's the difference between 98 Fahrenheit and 84 Fahrenheit? 14 degrees Fahrenheit, right? So we can actually calculate a difference. But what makes it an actual interval scale is that same difference means the same thing no matter where we are. A difference of 10 degrees is a difference of 10 degrees. Whether it's freezing, whether it's boiling, whether it's anywhere else in the middle, 10 degrees is 10 degrees. Okay, so that's an interval scale. And think about what the word interval means. Interval is some distance that we go, some time that passes, some chunk. So an interval is just saying that difference is an interval. So that's how you can remember interval scale. All right, and then the last level of measurement is what we call a ratio scale. This one is also quantitative. All right, so this is another one that you need numbers for. But again, it's data that's ordered. And has differences and ratios. All right, so the question is, well, what the hell do you mean by ratios? I'm sure you guys, I mean, you notice that's the next thing, right? We just added ratios, hence ratio scale. So all a ratio means is like if the number is twice as large, it's doubled, right? That would be a ratio 2 to 1, or it's tripled, or it's quadrupled, right? And so an example there would be like, let me show you why temperature is not a ratio scale. So think about this. Let's say it's 40 degrees out. Let's go Fahrenheit, because I know you're probably more comfortable with that. But let's say it's 40 degrees Fahrenheit. And then tomorrow it's 80 degrees Fahrenheit. Is it twice as hot? That doesn't even really make sense, right? Because 40 is cold, 80 is hot. It's not twice the temperature, right? Because there is no good zero scale, and we don't talk about that. We don't talk about something being twice as hot. But an example of a ratio scale would be like height, right? If there's a child who's 3 feet tall standing next to me, I'm 6 feet tall, I am twice as tall as they are. Not only can I calculate our difference, our height difference is 3 feet, but I can calculate the ratio between us. I'm twice as tall as that child. Okay, so just be aware that there are different levels of measurement, and these are just the words. So if you run across these, mostly I give you this stuff so that when you run across it, when you read something and they talk about it being ordinal, you go, oh, yeah. Ordinal means they're listed and there is a ranking, right? There is an order to it. That's really why I'm doing this, just because these words will pop up when we're doing statistics. All right, so let's get back to the how do we describe these different kinds of information? How can we actually put this stuff down? How can we group it so that it makes sense, so that somebody can take our study, take that data, make sense of it, and use it? So we're going to start with qualitative. All right, we're going to look at things that you can do to describe qualitative information. So since it's qualitative, that means we're not going to be doing things like finding the average. We're not going to be doing things like putting them in order necessarily, right? So different ways that you can show qualitative. All right, so this is going to be data organization. So the first one that you see a lot with qualitative is just a table. All right, so here's what we're going to do. We're going to do a qualitative study in our class real quick. I'm going to ask you to enter something into the chat box. It doesn't have to be truth, right? It doesn't actually have to be the answer for you. Like go back, remember that one on app when we were talking about the ages of people, first year college students. In that case, like you could give me your real age or you could give me a fake age, okay? I don't really care. That's not really what's important to me. So give me the actual answer if you want. If you don't, at least just give me an answer. But this is going to be a qualitative where we can organize the data. All right, and so what I would like from you is eye color. All right, so everybody in the chat box, type in your eye color, and you can make it up if you want. All right, wow, bam, coming fast. And I'll go ahead and include myself as well. I have blue eyes. You probably can't tell because of the darkness and whatever, but I've got blue eyes, so we'll add that to our list. All right. So let's just see what we've got. So starting at the top, we've got blue, blue, brown, brown. Let's make my list here. So blue, blue, brown, brown. Hazel, green, blue, green. Hazel, blue, green, green. Then we've got hazel and bluish. Uh-oh, is this one eye has each color? Is that what you meant, Ashton?
I have heterochromia.
Okay.
I have two different colored eyes. So that's
Okay.
what I meant.
So
Sorry.
that's what I thought, which I think is actually really cool. And I was not expecting that to happen, but we'll brown, brown, brown. Okay, so here's what we're gonna do. I'm gonna go ahead and take them as two different ones, just to make it so that we have a bigger list. So you say you have hazel and bluish, so we'll go ahead and call it blue. And then I was blue as well. All right, so here is a list of eye colors for the people that are in this group, okay, in this sample. Now, is it a representative sample of, say, people in California? Yeah, who knows? Probably not, but this is what we've got. All right, so here is a way that we could do this as a table. What I would probably do is I would make a little chart here that has eye color, and then the number of people with this eye color. So eye colors that we had that were responses, we had blue, brown, hazel, and green. I think looking at our chart, those are the four that we have. And if we count them up, blue, we've got 1, 2, 3, 4, 5. Brown, we've got 1, 2, 3, 4, 5. Hazel, we've got 2 and, or no, 3. And green, we have 2. Cool, that adds up to 15, which is how many we have. All right, so here is one way that you can easily represent this data so that it makes it so that somebody looking at this study doesn't have to sift through the entire list. Like you can imagine if I just gave this list and I was like, well, here you go, here's the data. Somebody would be like, that's nonsense. I don't want to have to look through all that. Where this is fast and easy. How many people have blue eyes? Ooh, 5 of them had blue eyes. And 5 of them had brown eyes, and 3 had hazel, and 2 had green, right? It's really easy to see what the representation is. And that's the goal of a lot of this, is putting our data in a form that's easy for other people to see, to read. All right, before I move off of this, I want to talk about another word we use to represent what's going on here. And this is what we call relative frequency. Actually, before I get to relative frequency, I should probably just talk about frequency. So in the context of statistics, frequency is how often something occurs. And so in our table here, this column that says the number of people, this is the frequency. Right, so the frequency of blue is 5. When we asked this question, we got the response blue 5 times. The frequency for brown is 5. The frequency for hazel is 3. The frequency for green, 2. Okay, so that's just frequency, is how often something occurs. But we also have what's called relative frequency. And the relative frequency, this is defined as the frequency divided by the sample size. It also could be population size, if we're talking about the frequency in a population, but we don't usually know the frequency in a population as a whole. We tend to know it just for our sample, but basically it's you take the frequency divided by the total number. So in this case, if we are going to look at relative frequency, I'm going to make one more column on my chart. Okay, so this is going to be relative frequency. So for the blue, it would be 5 out of 15. For the brown, also 5 out of 15. For the hazel, 3 out of 15. And for the green, 2 out of 15. So we took the frequency, we took how many times it happened, and we divided by the total number of responses. So we had 15 different responses. So we're going to take each of those and divide by 15.
And that's the relative frequency of each individual thing, right?
Correct.
Okay.
Yep. So the relative frequency of hazel is 3 out of 15. The relative frequency of blue is 5 out of 15, and so on. All right. So why do you think we would like relative frequency? What's the point of that? If we already have frequency, why relative frequency?
Because it's closer to your sample?
Well, it does tell us something about the sample. I don't know that it's closer to the sample.
Is it that you can narrow in on the study, kind of onto just the blue eyes or just the brown eyes?
I don't know how to answer that one because just the frequency itself kind of lets you do that as well, right? Like if you just wanted to key in on blue eyes, you go, well, there's those 5. How about this? Like, what is a fraction actually telling you? Oh man, I'm getting all mathy all of a sudden. I'm sorry, go ahead. Who was that? Well, how about this? What if I wanted to know what percentage of people have blue eyes? Right, that's a pretty common that's a pretty common question we ask, right? Or a number that we're looking for is what percentage do we get? That's what our relative frequency tells us. If you convert those fractions into percentages, that tells you what percent of this sample has blue eyes, right? So if we look at blue eyes, it's 5 out of 15, so 1 out of 3, 33.3%. So the relative frequency tells us that 1/3 of our sample has blue eyes. So if we're trying to use this sample to describe the population, let's just say population of people in the United States, we go from this sample, it appears that 1/3 of the people have blue eyes, right? Or it looks like 20% have hazel eyes, right? So relative frequency, this is giving us a ratio. It's giving us a percentage. It's giving us a proportion. Those are all different words for the same thing. But this is something that we're usually or very frequently curious about, is what proportion do we have? What percent do we have? Like think about all the statistical studies you hear about all the time, right? Especially during election cycle. It just got over. And they do things like, well, 47% of people favor candidate A. They just gave you a relative frequency, that 47%. They counted up all the people that were in favor of candidate A. They divided by the total number of the sample, got a relative frequency. Hey, that was 47%. All right, so it just tends to be one of those numbers that we use a lot when we talk about percentages or ratios. So just realize that all it is you're taking how many there were of that response and dividing by the total number of responses. All right, so for qualitative, we'll see this a lot. You see this sort of thing in studies all the time that show responses and their frequencies. Often their relative frequencies as well. Sometimes that's left for the reader because they'll tell you out of 15 respondents, we got this. So then you know to go, oh, blue eyes was 5 out of 15, green eyes was 2 out of 15, and so on. All right, so that's one of the things we'll do. We'll put it into a table. Another thing that we like to use when we organize data like this are what we call bar graphs. And bar graphs are a picture to help us see what's going on. And let's make a bar graph using this data. So I'm going to do it above the chart. I don't need the actual list of our data anymore because I've got my frequencies, so I know all of that. But here's how we do a bar chart. It is a graph. We're going to have a vertical axis and a horizontal axis. Now, on the horizontal axis, actually, let me move this up a little bit. This is where I'm going to put our eye colors. So I'm going to put them here in alphabetical order. So we've got blue, brown, green, and the hazel. Those were the 4 different eye color responses that we got. Now on the vertical axis, this is going to be frequency. And so I'm just going to do these 1, 2, 3, 4, 5, 6. All right, so this is how we do a bar graph. For blue, we're going to make a bar, a rectangular strip here that goes up to the quantity that we had for blue. So there were 5 blue eyes, so this is going to be a bar that goes up to 5. Brown, you're going to see exactly the same bar because we also had 5 responses for brown. For green, there were 2. So we're going to go up to 2 on the vertical scale to get our green. And then hazel was at 3. All right, so that's what we call a bar chart or a bar graph. Pretty easy. It still shows the same information, right? Like think about it, it's still telling us the same information. It's telling us the different eye colors, it's telling us how many were of each, but it's a picture. It's a picture. So why do you think you might want a bar graph instead of just a chart? Can anybody see the advantage of this picture up here?
It's a lot more visual.
It's definitely a lot more visual. So for visual folks, like I know I'm a real visual person. I love this. So it's great for visual folks. Think about this. How easy is it to look at this chart and tell me which eye color is least likely? It's pretty easy, right? If we're going to look for least likely, we just look for the shortest bar. Boom, that's green. Right? Otherwise, we'd have to go through this list and try to find the smallest number. Now, that's not too hard here because we only have 4 numbers. So I will give you that. With only 4 numbers, it's pretty easy to find smallest and biggest. But let's say there were 20 categories. Still really easy to look at a chart and go, which of these is tallest and which of these is shortest and all that. So it's really just, it's giving another way of seeing the data that can help certain people. And for those that are really visual, we like seeing it. All right, now I did mention that on that vertical axis that it's frequency, but it's not always frequency. Sometimes, instead of having frequency, sometimes we use relative frequency. So instead of using 5 and 3 and 2 as our numbers, we'd use the 5/15, the 3/15, the 2/15 as a percentage, maybe as a decimal, something like that. In terms of what this graph would look like, it's going to look identical. The sizes are still going to be all the same relative to each other. It's just instead of having 5 here, it would be 33.3%. Instead of having 1, right, it's going to be 1/15, which is what, like 0.0 or 5.5% or something like that. So that's the difference, is that it would just be our percentages. And so you'll often see it with relative frequency instead. All right, so bar graphs are another big useful one. And then the third one that we tend to use a lot are good old pie charts. And I bet you've seen these before. You may not know them by this name. But a pie chart is done by creating a circle. Pretend that that's a circle. Hence your pie. And what we're going to do is we're going to slice this pie such that the slices that represent the different eye colors, so we're going to have 4 of them. There's going to be a slice for blue, brown, hazel, and green, such that their slices take up the portion of the pie that's the same as their relative frequency. All right, so what I mean by that, for example, blue. Blue happened 5/15 of the time. That fraction reduces down to 1/3. So 1/3 of this pie is blue. I know my pen is actually purple, but we'll call that blue. All right. We also have brown is 5/15, which means 1/3. So 1/3 of this pie is going to be brown. So let's make that this side over here.
That was a good third.
Thanks. I think these are both a little bit more than 1/3 because this remaining third seems a little small, but not bad for freehanding it. I appreciate that positive comment as well. All right, so now we've got hazel and green. Well, if you think about this, is the remaining 5. 3 of those have to be hazel and 2 have to be green. So yeah, we'll go with that. So this would be our green is 2/15. And then our hazel is 3/15. So the pie chart does a lot of the same things that the bar chart does. It helps us compare sizes, right? It's another really easy visual way to look at this and go, oh yeah, blue is definitely more than hazel. Green is definitely the smallest, right? So it definitely helps us rank them. It's a really good visual for ranking them. However, what it does lose a little bit is the exact value. Like if all I did was show you this pie chart and I asked you what percentage is blue, it looks like it's around 1/3, but it may not be exactly 1/3, right? So we lose a little bit of information there. But it's also, it's very appealing. We like these for some reason. A lot of people use pie charts. But I do need to warn you about pie charts. Pie charts are good, but only can be used. So this is a little bit of warning that I need to put here. You can use these only when the relative frequencies add up to 1. I'm going to put it in parentheses, so that's 100%. So if you have relative frequencies that don't add up to 1 or 100%, however you want to think about it, you can't use a pie chart. So there are definitely restrictions on it, but they're useful when you are good, right? So where this will happen, where things don't add up to 1, is where you might get people that are in multiple categories. And this is actually a really good example. Trying to remember, it was Ashton, right, who has the 2 different eye colors. So if I hadn't listed those as separate, if I had just gone with people as our numbers, we still would have had 5 people that have blue eyes, 5 people that have brown eyes, 3 with hazel and 2 with green, but we don't have 15 total people. We only have 14, right? Because I don't know if you remember how I dealt with that when Ashton mentioned having the different eye colors. I was like, well, I'm just going to list them as 2 separate things, treating it like 2 different people because I didn't want to deal with that right then. But if we were going to be good about it and go, no, I have 14 respondents, And out of those 14, 5 have blue eyes, and 5 have brown eyes, and 3 have hazel, and 2 have green. Now all of a sudden, those things don't add up to 100%. They add up to more than 100% because we've got one respondent who is in 2 different categories. So, and that happens a lot, actually, when we do statistics out in the real world, that you'll get people that fall into multiple boxes. Another really good example is ethnicity, right? Think about all the times whenever you're filling out a form and it asks you for your ethnicity, and it'll say, check more than one if necessary, right? Because what if your father is Japanese and your mother's African American? What's your ethnicity? Well, I guess I would say African American and Asian, right? So you would check both boxes. You're now part of both groups. So there are lots of things out there where that comes up. So in that sort of circumstance, we can't use the bar or the pie charts anymore, but you still can use bar graphs. Bar graphs are totally fine, even if they don't add up to 100%. All right, so these are the 3 big ways we deal with qualitative data. It's really just we either do a chart with the data or we make some pictures, either bar charts. There are also some variations there where you just have lines instead of bars and things like that, but they all kind of break down to being bar charts or pie charts. All right, so I think at this point we're ready to move on to quantitative, but let me just do a real quick check-in. Any questions on any of these 3? We feeling okay? Thumbs up. All right. Cool, definitely seeing thumbs up. All right, let's take a break. I need to go get some water, so I've been talking here a while. Let's just take a break, go stretch and everything. It is 4:45 right now. Let's take 10 minutes. All right, so I'll be back at 4:55. You'll know I'm back when my image comes back up on the screen. I'll unmute myself and everything. But just take a few minutes, go walk around, grab a snack, and we'll be back at 4:55 to talk about how we deal with quantitative data. All right, so see you in just a few.
Good luck, Bruce. Ceremony.
Sermani, you there, buddy?
Hi, buddy.
Is my quality kind of garbo poo poo?
No, it's fine.
Oh, okay. Hi, Sermani.
What are you doing?
I'm gonna generate stone.
Excellent.
Mm.
Come here.
Howdy. Hi,
Hi.
Branda.
I'm Branda, but this is Miley.
Nice
Hi.
to meet you guys.
Hi, Branda.
Hello.
I know you.
This is
Another girl.
Stitchy. This is Stitchy
Woo! I know you.
Big ass husky.
Yeah, doggy.
All right, I'm back. Hopefully the rest of you start trickling in. And I saw that, Brandon, man, you got like a party going on over there, stats party. I love it. People can't get enough of it, right? All right, so let's go ahead now talk about what about quantitative things. How are we going to represent quantitative data, and the like? Before we go into the specific graphs and all that, I do want to mention the two main statistics that we tend to calculate when it's quantitative. And we kind of already hinted at one of them a little bit. Actually, I think we kind of hinted at both of them. But these are the two main statistics that are calculated. Just about everything comes down to one of these two. The first is the mean, and the second is a proportion. So when we have a set of data, quantitative data, right, where we actually have numbers, we tend to look at one of two things, either the mean or the proportion, or sometimes both. Now, the mean, this one, the general word for this is average. All right, so the mean of data is the average. It's the average height. It's the average number of pets. It's the average age. It's the whatever, right? And so we calculate this pretty easily. It's just add up all the values and divide by the number. Now, there are other kinds of means, and we will talk about them as we go, but the mean that we use is what we call an arithmetic mean. And it really is just add them up and divide by their quantity. Okay, so this is one of the things that we're going to tend to calculate a lot. And the other is the proportion, which is the ratio. Right, so this is a ratio, which tends to be a percentage. So this is the other big number that we'll look for, is the percentage. What percentage of respondents like candidate A? What percentage, what percent of people are vegetarian, whatever it happens to be. Okay, so these are the two big main statistics that we calculate. And just so that you're aware, it's going to matter which one we're doing in terms of what tests we do. But we'll talk about how we calculate each one of them. All right, but let's get back to then, how do we actually represent quantitative data? What are some different ways we can do that? All right. So I'm going to put here organize and display quantitative data. All right, so one thing we can use is a table, kind of like we did before with the qualitative. You can fill out a table. You can actually have a list of all the responses. Go back to that, average, the age of students starting out, whatever. We can make a table that says age, number of, frequency, number of responses, and so on. So we will use tables again. But one thing that's a little bit different with tables now is we'll tend to add another column when it's quantitative. So remember with the other ones, we had response, frequency, relative frequency. Well, there's another column that we're going to put in there, which is called cumulative relative frequency. Now, to do this one, we're going to poll class again. This is another one. You can share with me the actual answer, or you can just make up an answer. All right, so if you don't want to get too personal, that's fine. But what I'm going to ask for you to put in the chat box is your number of siblings. So not including yourself, but how many people in your family. So like I have 4 brothers, so we're going to put in a 4 for me. But the rest of you, if you would just put in the number of siblings that you have. So if you're an only child, put 0. So I'll give you guys a chance here to throw some numbers in there. All right, so we got some big families in here. So let's see what numbers we've got. I've got a number of 1, 1, 2, 1. So 1, 1, 2, 1. 2, 6, 4, 4. 4, 2, 4, 4. And we'll go ahead and put myself in there as well. Actually, no, we're going to leave it like this because this is a good number of people. This is a good number of responses. Okay, so we've got 12 responses. And I know it's probably blinded a bit by the reflection. Don't worry about it, but it's 1, 1, 2, 1, 2, 6, 4, 4, 4, 2, 4, 4. All right, so here's what this table would look like for this data. All right, so we're going to put here, in the first column is going to be number of siblings. Okay, the second column is going to be frequency. Then we're going to put relative frequency. And I didn't realize this, but I just made a dad joke. Get it? Relative frequency. Your siblings are your relatives. The unintentional dad jokes are the best ones, let me tell you. All right, so number of siblings, frequency, relative frequency, and then I'm going to put one more column here, which is the cumulative relative frequency. All right, so we have one more column. Now, I'll explain what that column is in a second, but let's start by filling this in with the actual responses. I'm a little bit surprised that nobody's an only child, because I was expecting a 0 number of siblings. I'm still going to go ahead and put that in. How many times did we get a response of 0? Well, it was 0. 1 sibling. There were 3 of you that said that. 2 siblings, there were also 3. 3 siblings, there were 0. And we got to get down to 6. So 4, 5, 6. So 4 showed up the most frequently. There were 5 responses of 4, no responses of 5, and 1 response of 6. All right, so those were our frequencies. So what are we going to divide by to get relative frequency? What number do I need to divide all these by? Good. Yeah, it's 12. Because we need to have, there are 12 response, right? There were 12 responses, so we're going to divide by 12. So this one's going to be 0 divided by 12. This is 3 divided by 12, 3 divided by 12, 0 divided by 12, 5 divided by 12, 0 divided by 12, and 1 divided by 12. So this is what they look like as fractions. But you also will often see these as decimals. Right? So 0 out of 12, that's 0. 3 out of 12 is 1/4, so that's 0.25. So this is also 0.25. This one's 0. 5/12 is 0.43. No, 41. If we round that to the nearest hundredth. 0/12 again is 0. And then 1/12, I believe, is 0.08. If you round it to the nearest 10. So it's not uncommon to see those things as decimals, just because that's really easy to convert to percent, right? So 8% of respondents have 6 siblings. 41% have 4 siblings. 25% have 2 siblings, and so on. Okay, so all of this so far is nothing new. It's exactly what we did before. But now that these are numerical and there's an order, right? This is now ordinal. It's actually also it's also an interval. It's also a ratio. It's actually all of those, but it's definitely ordinal. It's definitely ordered. What we'll do now is we'll use the cumulative relative frequency. Now, this is all you got to do to get cumulative relative frequency is add all the relative frequencies up to and including that point. So for 0, it's the first relative frequency is going to be the same as the cumulative relative frequency. Those two are always the same. Okay. Now the next one, we're going to add these together. 0/12 plus 3/12 is 3/12. For the next one, we're going to add up the first 3. So 0 plus 3 plus 3 is 6/12. The next one, 0 plus 3 plus 3 plus 0 is still 6/12. Then we go 0, 3, 3, 0, and 5. That's 11/12. The next one's going to be 11/12, and then the final one is going to be 12/12. So notice that all we're doing to get the next one is just adding that relative frequency, right? To jump from 3/12 to 3/12, we added this 3/12. To get from 6 to 11, we added these 5, and so on down the line. Now, as decimals, let me go ahead and put these in as decimals. This is 0. This is 0.25. 6/12, that's half. That's 0.5. 11/12, that rounds to 0.92. And then 12/12, of course, that's 1. All right, so again, I put them as decimals just so it'd be easy to see. percents. Now, why we like cumulative relative frequency is this. Like, what if I ask this question? What percentage of our sample has less than 3 siblings? Okay, so we had the sample. I want to know what percent has fewer than 3 siblings. Okay, well, that would be no siblings, 1 sibling, or 2 siblings. So that would be any of these. But this is how easy it is to determine. I want to know fewer than 3. Well, here is 3, right? If I want fewer than 3, it's the next number up. So I know that 50% have fewer than 3 siblings. Right, so this is a really great way for figuring out things like less than, more than, greater than, fewer than, because we've got sort of a running count, right? It's just like every time we get to another one, we add it to the list. We add it to the cumulative frequency so that we can kind of keep track. All right, so with quantitative data, this is definitely something we do. This is actually called a frequency chart, right? Frequency table. And we use it a lot. Just realize there is one more column now that there is an order to these things. You can also, if you've got them as decimals, you can actually just add the decimals to get the next one, so you don't have to do the fraction conversion. Just be aware that there might be some issues with rounding. It will sometimes play out where if you add up the decimals, you don't get exactly the same thing on the other side. You're off by like 1 wherever the rounding is because of rounding. So don't freak out. Like this one, it says 0.92, where if you actually add them up in this column, you get 0.91. That's just a rounding issue. It's not a we did something wrong. It's just a rounding issue. All right, so tables, they're great. We can use them just like before. All right, but there are some other things that we can do with these, some other kinds of representation of this data. The next one is very similar to the bar chart, but this one's called a histogram. And we're going to make a histogram of this data. All right, now histograms, unlike the bar charts, you may remember with the bar charts, we did this with the eye color. We just went with, here are the categories: blue, green, hazel, brown, right? We have those eye color categories. Now our categories are numbers. They are ordered. So we're going to put them in order just like we do any other number on the real number line. Okay, so in terms of number of siblings, let's start drawing our chart here. So down on this axis, this is going to be the number of siblings. Right? I've got 4 siblings. Some of you had 1 sibling, right? So this is going to be number of siblings. And again, on this one, this is going to be frequency. So you can see how this is starting to look a lot like the bar chart. All right, but now what we need to do is we need to make intervals. We need to break this up into intervals, and we want each of those intervals to contain the numbers of siblings. Okay. So for this one, how I'm going to break this up is instead of, well, here, let me put 0, 1, 2, 3, 4, all the way out to 6. So here's 1. I'll try to scale it nicely here. So 2, 3, 4, 5, 6. Okay. But what I want is my histogram. I want my bars to be centered at these numbers, and I need them to meet each other. So that means like the bar that goes around 1 needs to come out here to 1.5 on the right and 1/2 on the left. The interval around 2 needs to be 1.5 to 2.5. For 3, it's 2.5 to 3.5, and so on. All right, so for this histogram, the intervals, they need to be, well, they don't need to be, but what we usually do, the intervals are centered and have the same width. This same width isn't always the case. It's not that they always have the same width, but we tend to do that, especially for something like this where it's discrete, where it's a counting number. All right, so here's how this is going to play out. We're going to put bars here of the right height for the different frequencies. So in terms of the frequencies, let me just put some marks on here. So we've got 1, 2, 3, 4, 5. Nothing happened more than 5 times. So this is what this one's going to look like. 1 occurred 3 times. So we're going to put this bar that goes from 1/2 to 1.5 and give it a height of 3. All right, 2 also showed up 3 times. So it gets the same height bar. 3 didn't show up at all. So we'll actually leave that blank. Sometimes you'll see a line drawn here. 4 showed up 5 times on our list. So that bar is going to be a little bit taller. 5 didn't show up at all. And then 6, there was one person who said they have 6 siblings. So there you go. So this would be a histogram for our data. Like I said, it looks a lot like a bar chart. It's just these bars come together. They actually touch each other. And the touching is especially important when it's a continuous measurement. Remember continuous versus discrete? Discrete was you can count it. Number of siblings you can count. Continuous was, no, you can't count it, but you can still measure it. So like height, weight, length, things like that. All right, so histogram, another big way that we organize and display quantitative data. So these two, very much the same as what we did with the qualitative. So now let's look at some that are specific to quantitative. All right, the next one I want to show you is what we call a box and whisker plot. All right, so box and whisker plot. Sounds kind of weird, right? Box and whisker plot. Well, with a box and whisker plot, we actually have to do some calculations. We need to do some calculations to actually construct our box whisker plot. Now, here are the box and whisker plot always has 5 things in it. There are always 5 pieces to any box and whisker plot. And we'll talk about what we have to do to find all of these. All right, so we need 5 things. All right, the first is a minimum value. So we actually need to know the smallest value for our data. This is always really easy to find. You just look at your list, what's the smallest one? Boom, that's our minimum value. We also then need the maximum value. Also really easy to find. Look at your list, what's the biggest one? So like if you look at the list of the data we just found or that we got for number of siblings, the smallest, the minimum was 1, the maximum was 6. Okay, well, there you go. We've already got 2 of the 5 numbers we need. So these 2 you get for free. All right, the third that you need is the mean. Okay, so you need to know the average of these guys. All right, now to get the average, it's pretty easy. I've mentioned it a couple of times, but let me go ahead and write down how we calculate the mean. All right, if you want to get the mean, it equals the sum of the data divided by the number in the sample. Okay, so this would be if we're talking about the mean of our sample, it's add up all the data and then divide by the number in that sample. All right, so for this specific example, you would take 1 plus 1 plus 2 plus 1 plus 2 plus 6 plus 4 plus 4 plus 4 plus 2 plus 4 plus 4, and you would divide that by 12 because we had 12 responses. All right, so in this case, and let me actually show you the symbol that we use for the mean. So when we're talking about the mean from a data set, we use the symbol, we call it X bar. It's an X with a little bar across the top. All right, so this is your sample mean. We have a different symbol for the population mean that I will show you later. But for the sample mean, just X bar. All right, so for our data here, let's see what that is. So X bar is going to equal, again, just add them up. 1 plus 1 plus 2 plus 1 plus 2 plus 6 plus 4 plus 4 plus 4 plus 2 plus 4 plus 4. And we're going to divide that by 12. So let's see, we got 4, 8, 10, 22, 28, 30, 32, 33, 34, 35. So it's 35/12, which is going to be 2. Let's see, and 11/12 is 2. We'll just go to the nearest tenth. So it's 2.9. So the average number of siblings for someone in our class that responded to this is 2.9. All right, now this is actually good. I'm glad we didn't get a whole number here because this happens a lot. That even if we're looking at data that's discrete, countable number of siblings, it's possible for some of these other quantities to not be countable. They can be decimals. Okay, so don't let this freak you out. It's totally fine. Just on average, we have 2.9 siblings. If you want, you can round it to the nearest, and you say, so on average, people have 3 siblings. But that's the mean for this data set. All right, so that's the third thing we need. So we have a minimum value, a maximum value, we have a mean. And then the last 2 that we need, oh, totally lied to you. I really apologize for this. We don't actually use the mean. I got all excited about mean. We use what's called the median. Well, let's go back and get it. Oh. Okay, we use the median, not the mean. But hey, we calculated the mean. Yay? No. All right, so the median. What's a median? So the mean we saw was the average. The median, this is the value such that half of the data is greater than or equal to it, and half of the data is less than or equal to it. So basically, it's the number that splits our data into two, where half of the data is bigger than it and half the data is less than it. It's the middle point. It's the middle point in our list. So let me show you how to calculate the median. It's actually really easy when you have a list. So let me list out this data again where it's not being blinded out here by the light. And I'm going to list it in order. So we had 3 responses of 1, 3 responses of 2, 5 responses of 4, and 1 response of 6. So there were our 12 data points. All right, so since I have 12 data points, for the median, I need 6 above it and 6 below it. So I'm going to go count 6. I'm going to come down our list 6. So 1, 2, 3, 4, 5, 6. And I'm just going to put a line right here. All right, so you see that orange line? That's where we split the data into 2. All right, so the median is right there. Now, how you get the median depends on something here, and it depends on whether or not that middle lands on one of our data points or doesn't, right? So like if you look at this, this middle does not land on a data point. It's exactly in between 2 and 4. So the way that we actually calculate this median is we take the average of these two numbers. So for this set, the median is going to equal 2 plus 4 divided by 2, the average of these two guys. All right, well, 2 plus 4 is 6. 6 divided by 2 is 3. So the median of this data is 3. All right, now sometimes when you try to cut the data set in half, it doesn't get cut in half evenly, right? We had an even list here. What if we had an odd number of responses? So let's say we did the same thing. All right, and these were the 9 responses we got to how many siblings do you have. Now, here's the problem, of course. If I take 9 and I divide it by 2, I get 4.5. And I can't go exactly 4.5 spots, right? If I started going down, I could go down 4 spots. 1, 2, 3, 4. Bring me right here. Going up 4, 1, 2, 3, 4, brings me right there. And notice that there is a central number. When this happens, that central number is our median. All right, so let me go ahead and write this down in terms of how you find it. And it all depends on our number of data points. All right, so let's let n be the number of data points. Okay. So here's how we find the median. If n is odd, the median is the middle value. So if we've got all our data listed out, it's the middle value. So in this case, it would be 3. If n is even, the median is the average of the 2 middle values. And that's what happened here, right? The 2 middle values, if we just start counting from the outside and working our way in, we get to these 2 middle values. You take the average of them, and that's how you get your median. All right, so I apologize about that mean thing. It's still important you know how to find the mean, because we need to know how to do it, but I'm sorry I confused. We need the median for the box and whisker plot. All right. Now, the last 2 numbers we need are what we call the first quartile and the third quartile. We don't usually write out these words. Instead, what you'll see when we're talking first quartile and third quartile, you'll see Q1 and Q3. All right, so what the hell are the first quartile and the third quartile? Well, what they are, they're the medians of the first half and the second half of the data. So this is the median of the first half. And Q3 is the median of the second half. All right, so it's the midpoints of the first and the second half. Basically, what that means is that these quartiles break us into quarters, because half of a half is a quarter. So basically, you can think of it this way. The first quartile is such that 1/4 of the data is less than or equal to it, and 3/4 is bigger. The third quartile, 3/4 is less than or equal to that number. Okay, so that's how quartiles work. So if we want to find quartiles, we're going to do the same thing, but just looking at the top and bottom halves. So let's look at our data again. And we've already split it into half. Let me just rewrite these numbers 4 and 2. So let's look at the top half. So the top half, if I were to cut it into half, that split's going to happen right here. There are 6 numbers in that top half. So if I split that into 2, that's 3 and 3. So my first quartile has to land right in here. Okay, if we look at the bottom half, do the same thing. There are 6 in that group. I have to cut it in half. So that's going to happen right there. And so that's going to be Q3. So Q3 is going to be right there. So just look at Q1, the median, and Q3, and you see what it's doing. It's just splitting this thing up into 4 pieces. Splitting it into 4 chunks. Each of them is 1/4 of the data. Okay, well, let's get the numbers here. We saw that the median was equal to 3 because it was the average of those 2. So let's go to Q1. Same thing happened. the first quartile landed in between two numbers, so we have to take its average, their averages. So if we average 1 and 2, 1 plus 2 is 3, divided by 2 is 1.5. So the first quartile is 1.5. The third quartile, well, it lands between two numbers, which are 4 and 4. Well, if you take those and you average them, you get 4. If you ever end up with this, where your median or quartile or whatever our cutoff is between two numbers of the same value, that is your answer. Because when you average two numbers that are the same, you get that number. Whew, okay. So we have the 5 things that we need for our box and whisker plot. Finally. Now let's put it together. All right, so here's how the box and whisker plot looks like. You start with a box. And then you add to it whiskers. Okay, this is why it's called a box and whisker plot. Now, where everything goes, because remember I told you you need to know 5 values to do this. In the middle of the box is our median. So that's going to be somewhere in the box. The 2 edges of the box are going to be our quartiles. And then the ends of the whiskers are going to be our minimum and our maximum. So that's why we need these 5 numbers. They help define our box and whisker. 3 of them are used for the box, median and 2 quartiles. And then the ends of the whiskers come from min and max. All right, so let me show you what the box and whisker plot for our data would look like. So I'm just going to make a real number line here again, and I'm going to kind of split it up so it's nice and even. Okay, so here is 0, 1, 2, 3, 4, 5, and 6. All right, so let's make our box and whisker plot. So I'm going to start with the box, and I'm actually going to use the quartiles to create my box itself. So my quartiles, the first quartile was 1.5, and the third quartile was 4. So my box is going to go from 1.5 to 4. Let's draw in our median. Our median was 3. So I'm going to draw in my median. You usually see it as a dashed line, but it can be a solid line. It's pretty well understood what's going on when you've got a box and whisker plot. But there's our median. And then I need to draw my whiskers out to the minimum and to the maximum. So the minimum was 1. So I'm going to draw my whisker out here to 1. And my maximum was 6. So there's a box and whisker plot for our data. Now, if I gave you different data, obviously this would look a little bit different, but it's always built the same way. The box goes from quartile 1 to quartile 3 with the median marked, and then the whiskers go to minimum and maximum. All right, so what's the point of this? Why have this picture? So what? Well, just like before, this is a real visual representation of this information, right? We can look at this picture and we can see everything. We don't have to go sifting through the data. Instead of worrying about this big long list and everything, that work's already done. I can just look at this, go, oh, okay, the median is 3. Oh, the maximum value is 6, right? We've got that information right there ready for us to grab. But even more, it actually tells us a little bit about the data. And let me just show you some interpretations. So first of all, look at the whiskers. Notice how the whiskers have different lengths, right? This whisker was kind of short, the other one was kind of long. Well, if you have a long whisker, if one of those whiskers is long, what that tells you is that the maximum or the minimum value is kind of is what we call, well, not technically, but the common word is outlier. Like, it's unusual. If you've got a really long whisker, it means that that data value is a little bit weird. It's quite possibly an outlier, right? Now, in our example, 6 isn't really that crazy, right? Having 6 siblings isn't unheard of. But you can imagine, what if we asked this question and the maximum number was 60? And someone said, ooh, I've got 60 siblings. That would be weird, right? That would be extremely unusual. That would give us a really long whisker, which me looking at this would go, whoa, that's weird. We got some issues going on, right? So the whisker lengths will tell you something, right? Like this one, the fact that this whisker is really small means that my minimum value is not rare at all, right? It's not really a rare number. Now check out my box and notice how the median isn't actually in the middle of the box. That tells me that my data isn't evenly distributed. And the fact, because it's towards the right of the box, it tells me that my data, that there are more bigger numbers than smaller numbers. And if you look at our data, you can see how it is definitely shifted towards larger numbers. These 4s and 6s, those are a lot bigger relative to the median than the 2 and the 1. So that's also something that it will tell you. It tells you how the data is skewed. Skew is a measure of how far we are, if the data is more collected centrally versus to the left or to the right. And so this data is definitely skewed. There are more bigger numbers, right? So there are a lot of things that you can actually interpret from a box and whisker plot when you get good at looking at them. And I know for you right now, it's like, whatever. Yeah. The more you practice it, the more you'll definitely see how to interpret these kinds of plots. All right, before we leave these, there are a couple other pieces of information I want to give you. The next one is what we call the Inter-Quartile Range. And that is often written IQR. Okay, so the Inter-Quartile Range. And it's a real easy calculation. It's just Q3 minus Q1. So think about what the word says. It's the Inter-Quartile Range. Inter means between. Range is, distance, whatever. So it's basically the distance between quartiles. So with our data set, the IQR is 4 minus 1.5, which is 2.5. On a box and whisker plot, the IQR is the width of the box. So the total width of the box is the Inter-Quartile Range. Now, with the Inter-Quartile Range, we actually can define outliers. Okay, and this is definition of an outlier. We already know outlier means it's something that's kind of far away from the rest of the data. But an outlier is a data point at least 1.5 IQRs from the box, or from the mean, DN, median. No, from the box. So basically what you're looking for are any numbers that are more than 1.5 times this interquartile range from either the first or third quartile. So 1.5 times this would be 3.75. So an outlier would be something that's more than 3.75 away from 4. So like 8. If we had somebody say they have 8 siblings, that would be technically an outlier. On the other side, it's never going to happen because from 1.5, we're not going to be able to go far enough away. But it's possible that depending on the data set and what numbers we're calculating, that you might be able to go that far in the other direction as well. So we use that interquartile range to actually determine outliers. It gives us a measure for how far is too far. All right, so there's your interquartile range. The last thing I want to mention about this, or that's related to this, are what we call percentiles. And a percentile is very much like a quartile. In fact, a quartile is a specific one. All right, and so percentile, what you'll see is, for example, they'll say something like the 90th percentile. One place I remember seeing these were on standardized tests. I don't know if you guys remember when you've taken like, if you've taken the ACT, the PSAT, you know, or any of those coming up along the way, you get those scores back, right? And it'll be like, in English, you're in the 87th percentile, and in math, you're in the 92nd percentile, and in science, you're in the 73rd percentile. That's where one place I definitely remember seeing those. But percentile, basically what this means, if you're in the 90th percentile, this means that 90% of the data is less than or equal to that number. So remember those 3 values we found to form the box? The median, the first and third quartiles? Those are also percentiles. The median, it's the 50th percentile, right? It's the one that splits it so that half is less. Q1, this is the 25th percentile, because 1/4 is less than that number. Q3, this is the 75th percentile. So while the median and Q1 and Q3 are special percentiles, you can actually break this down to anything. And just go, I'm going to go with I want the 80th percentile. I want the 37th percentile. It just means this is the number such that whatever percentile is less than that value. All right, so there's a little bit more about Box and Whisker. Looking at the clock, I see I have a little bit of time left, but I'm actually going to stop here. I think this is a good place to end for today. So we're still in the middle of chapter 2. We're a little bit behind the schedule as we have set, but don't stress about it. I'm sure we're going to be totally fine. But what we're going to talk about on Thursday, we're going to continue this discussion. And we are going to talk about centralizing, or we're going to look a little more in terms of some other ways of describing data, like we have to look at what's called a stem and leaf plot and stuff like that. But then we're going to look at other things like, well, we looked at the median today, talked a little bit about the mean. Well, we'll compare those. We'll look at a third way of kind of looking at centralness of data, which is called the mode. Then we'll look at how we spread data and keep on marching on. All right. So with that, let me go ahead and pause the recording.